Okay, here's a review problem for exam 2 that looks a lot like the problems we had for exam 1. But remember, all this stuff is cumulative, and so we are still responsible for knowledge that you needed from exam 1. Plus, you can approach this problem from a z-transform point of view, and we didn't have z-transforms as a tool back on exam 1. And so in some sense, the problem is easier using z-transforms, in my opinion. So let's go through this real quickly. Remember, on an exam, time is important, okay? So don't get hung up on calculations. You can just set everything up, and then if you have time to go back and punch things into the calculator, that would be fine. But, you know, try to work through things quickly. All right? So I'll talk about that as we go through. But anyway, let's go through the solution. Step 1 here, or part A, we're looking for the transfer function of the system. Well, by now, we can write that down by inspection. We know that h of z is the b coefficient. There's only the single 1 for the b coefficient. And then we divide by the a's. Okay, so we have a delay. We have 1 for y of n. We have 1/10, a delay of 1, minus 3/10 with a delay of 2. So there we go. There's our z transform that gives us the transfer function of the system. Okay, so your next step is to quickly come up with the roots. And the reason you're going to need the roots is for the next part. If you're going to find the impulse response and the step response, you're going to need the poles of the system. So you can find these roots in any way that you want. There's C-solve, there's the quadratic equation, there's just by inspection, you can kind of look at this one and factor it if you're good at that kind of thing. But plug that in, there's a root function on your calculator. Plug that in and you can show that the poles are at 0.5 and minus 0.6. Okay, so finding the poles alone is not necessarily good enough. Sometimes there might be a scale factor involved, but if this first coefficient here is a 1, then typically things work out fine. You can just write this down as a factor of pole locations. Okay, there were no zeros in this problem. You wouldn't need to mess with the zeros if there were, because you only need to do partial fraction on the denominator, not on the numerator. Okay, so writing this down, we know there's a pole at minus 0.5, at 0.5, so this would be 1 minus 0.5, z to the minus 1. I go straight to it. I don't have to think. I just know that's the result, okay? Then there's a pole at minus 0.6, so 1 minus a negative 0.6 is plus 0.6 z to the minus 1. There we have it. Okay, this is all set up and it's ready for a partial fraction expansion to find the impulse response. So the key piece of knowledge that I'm assuming you know, that here is h of z. If we do the inverse z transform of the transfer function, we get the impulse response. Okay, so that's where we're heading. We do set up the partial fraction expansion. So this is the kind of work I expect to see in your exam page. There's the partial fraction expansion. Okay, from here, you use the cover-up method. All right, the cover-up method should go quickly. So remember, if you want to find the a factor, cover this up. And where does this have a 0? Where is this a 0 in terms of z to the minus 1? Okay, so if you take z to the minus 1 equal to 2, 1 minus 0.5 times 2 is 0. Okay, so that's the number you plug in, and you cover up the part in green, and so what you're left with is 1 plus 0.6 times 2. That's it. That's the partial fraction expansion. You could just stop right there on an exam and leave the rest of it in terms of numbers. That shows me that you know how to get it to a number. It's sometimes easier to go ahead and calculate this so that you can write everything down in a more compact form, but you can plug this into your calculator, and 4 digits is good enough. understand you're under time crunch, so coming up with the fractional equivalent is not necessary. Okay, so same thing for part B. Part B is a little trickier looking because what you want is z to the minus 1 equals 1 over 0.6. It's just 1 over this number is what you plug in for z to the minus 1. So I'm going to plug that in to, I'm going to use the cover-up method, all right, to find B. So I no longer cover up this screen part, I cover up this screen part and plug into what's left. Okay, so that would be 1 over 1 minus 0.5 negative 1 over 0.6. I forgot the minus sign. Because it's a plus, that would be a minus sign here. Okay, and so you can go through this and just plug it straight into your calculator if you'd like and take it to 4 digits. And this is what we would get. Okay, all right, so from there you could write, you can see what I've written here in a lighter shade here, but you could write this out as A times 0.5 to the n plus B times minus 0.6 to the n u of n, and you've already specified A and B, so you'd be good to go. All right, you can consider that part solved. Okay, so those are some time hints, and of course, the idea is you already know exactly what to do on each part, and so you can do it pretty quickly. Okay, all right, so for part C. For part C, I'm asking for the step response. I'm not asking for the steady state response, I want the total solution. So it's a Z-transform problem. Remember, for all this work, we're assuming the initial conditions are 0. There's a way to make the Z-transform handle things where initial conditions aren't 0, but it involves the one-sided Z-transform. We haven't covered that. So on all the problems like this, you'll have initial conditions being 0. Okay, so y of z, we know from the convolution property that y of z is going to be h of z times x of z. It's a unit step as the input, so x is equal to a unit step. I can look this up. Actually, I should have this on my formula sheet. The z-transform of a unit step is 1 minus z to the minus 1. Okay, so we can write this all out. I know then this would be the overall z-transform of the output signal y. It's just the product of those two z-transforms. Okay, so that leaves us with a over 1 minus 0.5 z to the minus 1. We're going straight to partial fraction expansion. You've done this a lot. You did it in differential equations, you did it in signals and systems, you did it probably in control theory, and now you're doing it again. Partial fraction expansion. So we can work that pretty quickly. The cover-up method says that the a would be, I'm plugging in z minus 1 equal 2, covering that up, and what's left is this. Okay. Plug that into your calculator to 4 places, and this is what you get. For B, remember, z to the minus 1 is 1 over 0.6 with a negative sign. So I cover that term up, 1 over minus 0.6, and plug in to what's left. Okay, and I get that to be this number to 4 places. And finally, the C value, you have z to the minus 1 equal to 1 in that case, right? Because you're zeroing out this term. Okay, so moving on with that, it's 1 minus 0.5 times 1, 1 plus 0.6 times 1. Okay, so when you plug that into your calculator, you get 1.25. All right, so it is important on your exam to sum it all up. So y of n is minus 0.45, 1/2 to the n, plus 0.2045, minus 0.6 to the n plus 1.25. All right, so there we go. That's the step response. Okay, now for part D, all right, part D, you have to read things carefully. I'm asking for steady state response in this case. I could also ask questions about stability. Since this is if you assume this is a causal system, it would be stable, and therefore it would have a steady state response. Okay, so moving on, we know there's a critical z value to evaluate for the steady state response. You evaluate it at e to the minus j pi over 3, because that's the frequency. Go back up to the problem statement. That's the frequency of the input signal x of n. Okay? All right. The magnitude of x was 1, so cap x is 1. And what we then look at is this complex number, y steady state. That's going to be h times z naught. You can plug this into your calculator, and you get, if you put it in polar form, 0.8248 at angle minus 0.1433. Okay, so this would be in radians. Your calculator needs to be in radian mode for this to work. Okay, you don't need to convert that back to degrees either. So from here, you write down the final answer. Y steady state is 0.8248 cosine pi over 3n minus 0.1433. Okay, so I might not ask you everything on a problem like this for an exam because it takes a while to grind through it, but you should know how to do all these parts coming into exam 2. Okay, I wanted to also show you something in MATLAB. We just worked sort of a system input-output problem in an exam review, and so I wanted to show you that you can work as many of these as you want, all right, and you can check your answers because it's pretty easy to get MATLAB to do these calculations using the symbolic toolbox. Okay, so I wanted to run through that pretty quickly. So the first thing you need to do if you're interested in doing this is declare symbolic variables, and then you define h. Okay, so pretty easy that you define h. You didn't really even have to find the roots because the symbolic toolbox is going to do that for you when it calculates the inverse z transform. All right, so inverse z transform, there you go. MATLAB's assuming a one-sided z transform, so you'll notice there's not a unit step function out front because it's implied. And it has to be greater than or equal to 0 for MATLAB calculations. Okay, and then next, of course, what we did was we asked for the step response. So I plug in h. All right, let me clear that. H, and you multiply by the z transform of the step. Okay, so this is what shows up in MATLAB. You do the inverse y, and it gives you the exact answer that we calculated sort of by hand before. All right, and then of course it's easy to check steady state calculations in MATLAB because you can just evaluate the transfer function at whatever z value you want, get the steady state magnitude, then find the amplitude and the phase to make that final calculation work. So I just wanted to point that out in case you wanted to, if you're not confident in that part where you're calculating partial fractions or whatever, you can use this kind of approach to make up your own problems and